Hey AP Chem, welcome back to Kinetics Part 4. Today we're going to talk about reaction mechanisms. So we've referenced this a little bit throughout our notes, talking about how the reaction rate, the rate law, can't be written from the balanced reaction, right? You cannot write a rate law by only looking at the balanced reaction. You must base a rate law off of data, right? And that goes back to this idea that we don't know what the mechanism is of our reaction. So let's look at what this means. What does it mean to have a mechanism? So let me give you an example. Okay. Let me find an example for you. Okay, here's one example for you. You can see here on this slide, there's an overall reaction. And this overall reaction seems to suggest that two ammonia molecules collide with an NaOCl. So that's sodium hypochlorite. And if these three molecules collide, then they're going to break each other apart and then reform into the products, right? So that's what this overall reaction suggests. Now, does that actually happen? So what I just said was that the NH3 molecules, NH, H, and there's two of those. They're going to collide with each other and with this NaOCl molecule. Okay, so what I just said is that all three of them are going to collide at the same time. Then they're all going to be broken up into their components, right? We're going to have a whole bunch of H's floating around, 6 to be exact. We're going to have a whole bunch of nitrogens floating around. We'll have some sodium, we'll have an oxygen, and we'll have a chlorine. So all of these things separately are going to be floating around, and then they reform into the products. So what I've just done is I've just proposed a mechanism to you. My mechanism is that I go from my reactants to all my atoms to my product molecules. But does that actually happen? Maybe not. Maybe instead of going to all of the atoms, maybe the, let's see, what could possibly happen? Maybe the nitrogens form together. So we get this N stuck to another N with all of these H's. So I just stuck my two ammonias together. Okay, so this is proposed mechanism number 2. And then my Na, my O, and my Cl all break into atoms. Maybe that's what happens. And then they reform into products. So who knows? Who knows how the product or how the reaction actually proceeds? How the reaction actually proceeds is called a mechanism. That's what a mechanism is. And you will not ever be responsible for proposing a mechanism. What you will be responsible for, what I'm about to teach you how to do, is how to defend a mechanism. Is this a probable mechanism? Could this mechanism actually happen? Okay, so that's what we want to look at. Now, there's a couple things that come out of this that we're going to talk through. First of all, before I clear my screen, let's talk about what's up here. Notice that the reactants are present, and the reactants in either case are going to go to something, whether it's all the atoms or whether it's new molecules. The reactants are going to turn into something that's not actually represented in the overall reaction, right? Notice nowhere in this reaction does it ever list all of these atoms separately. Nowhere in the reaction does it ever list a giant molecule where two ammonia molecules are stuck together. These things aren't listed in the overall reaction. And what we call these things that might occur, might exist as the reaction proceeds forward, but then they're also used up. So they're created, then they're used before the reaction finishes, and we don't actually list them in the overall reaction. Those things have a name, and that name is intermediate. Those things are called intermediates. Okay, they could be created and then used up, but they don't exist in the beginning of the reaction. They don't exist in the end of the reaction, but they have to exist so that the reaction can proceed forward, right? Those things are called intermediates. So that's one thing to be aware of. In mechanisms that are proposed, you're going to see some intermediates. And let me show you one from this example. Okay, so far, they've given you an overall reaction. Fun fact, this is called the Raschig process for the preparation of hydrazine. So if you are in the hydrazine business, you're going to produce some hydrazine and sell it off. This is the overall process for that. Okay, so that would be the overall reaction. Now, here, let me show you a proposed mechanism. Proposed mechanisms can be verified or, well, they can't really be verified. Proposed mechanisms, we can either say, no, this one can't exist, or we can say, this could exist. But we really can't stand here and say, this is the one. This is exactly how it proceeds, okay? So that's what we're trying to do. As we look at this proposed mechanism, what we want to try and do is say, yep, this could be a possible proposed mechanism, or no, this could not be a possible proposed mechanism. So let me show you what a mechanism looks like. First of all, it's going to occur in a couple different steps. Notice this one occurs in 3 steps. Second of all, notice there's some intermediates in here, right? Okay, so NH3 exists in the beginning. It shows up in 2 of our steps. NaOCl, this one actually shows up as the ion. And the reason they do this is because as soon as this gets put into an aqueous solution, it's a highly soluble salt. So NaOCl is not actually going to exist in solution. Na will exist and OCl minus will exist. But NaOCl minus won't actually exist. So that's why you don't see NaOCl minus listed down below. You do see the OCl minus listed down below. And notice that they completely ignore sodium. Sodium doesn't appear anywhere in these 3 steps. So what would we call sodium? Sodium is a spectator. Sodium's floating around in the beginning. Sodium's floating around in the end. Sodium's not actually used, created, or destroyed. Well, I guess nothing's actually destroyed, but it's not used at all in the reaction. It's a spectator. So they just omit it to make the whole overall thing more simplified. Okay, so we can see in our 3 steps where our reactants are. Now let's look for our products. Okay, N2H4 shows up here. NaCl, again, highly soluble salt. It's going to split into Na plus and Cl minus, which are the 2 things that are going to exist. NaCl doesn't actually exist in the solution. So again, Na is the spectator. It gets ignored. Cl minus is the one we're going to see in here. So there's Cl minus, and then H2O shows up here. Okay, so you can see our reactants. You can see our products. Now notice everything else. Everything else is an intermediate. NH2Cl doesn't actually show up anywhere in our overall reaction. It's created in step 1. It's used in step 2. Same thing with OH minus. OH minus doesn't actually show up in our overall reaction. It's created in step 1. It's used in step 3. So this one gets used up. This one gets used up. Here we have a third intermediate, N2H5 plus, not actually in our overall reaction. It gets created in step 2. It gets used up in step 3. So these are our intermediates. They're created in one step, they're used in another step, and they're not actually included in the overall reaction. So why do we include them at all? Well, usually we don't, right? Usually, up until this point in our chemistry career, we have only dealt with the overall reaction. We've never actually dealt with reactions that have intermediates. And, fun fact, after kinetics, we won't deal with mechanisms anymore. And so we're not going to deal with intermediates anymore either. So usually for all of our other purposes, like, do we want to know the energy of a reaction? Do we want to know the neutralization? Do we want to know what precipitates out? Do we want to know how it affects gases? Do we want to know what kind of things, what kind of conditions we can use to manipulate the reaction? We actually don't need to know about intermediate for any of this. Looking at the speed of the reaction is our one concept where it's useful to know about intermediate. So that's why we're seeing it now. We've never seen it before because now we're very interested in talking about the speed of reactions. And if you're in industry or you're a chemist that works for an industry, you're going to be very interested in talking about speed of reactions because how fast you can make something is how fast you can make money, basically. Okay, so now we see what a mechanism looks like or could look like. We see what intermediates look like. Now I want to back up and give you just one more vocab word before we kind of get into how to evaluate proposed mechanisms. Okay, so the vocab word is talking about the molecularity of each step. So in the proposed mechanism, we had those 3 steps. Well, the number of molecules involved in the step is what we call the molecularity of the step. So let me show you some examples of that. This would be a unimolecular step because there's only one molecule on the reactants side. So bimolecular would have 2 molecules in the reactant side. Termolecular would have 3 molecules on the reactant side. And this is the implications of this are go back to the kinetic molecular theory. So here's a bimolecular. Notice there's 2 molecules involved in the reactant side. Notice those 2 molecules are the same, which is fine. So if you have something, we would not normally write it like this. We would normally write it like 2Hi goes to H2 plus I2. So this, because there's 2 reactants, even though they're the same reactants, there's still 2 molecules that have to collide in order for this reaction to proceed forward. Okay, that'd be a bimolecular step. And then a termolecular, notice, has 3 molecules that have to collide. So this is where it gets back to the kinetic molecular theory. In order for this reaction to proceed forward, the number of molecules in the step, they actually have to collide with enough energy and the right orientation in order for this to move forward. So a unimolecular step doesn't actually have to collide with anything. And ozone's a good example of this because the ozone decomposition that you see right here is actually catalyzed by sunlight. So radiation hits this molecule, and because of the absorption of energy, the molecule falls apart. In the case of the hydrogen iodide or hydroiodic acid, the two HI molecules have to collide with enough energy and the right orientation in order for this to proceed forward. And then in the termolecular step, what has to happen is that all three molecules have to collide at the same time with the right energy and the right amount of orientation in order for this to proceed forward, which is really rare. Like, what are the chances of the right three molecules colliding all at the same time with the right amount of energy and the right orientation? It's going to be a rare phenomenon. And if it happens, it probably has a catalyst at work. So we've dropped this word catalyst a couple times. We're going to revisit catalysts after we talk about mechanisms, but basically what a catalyst is it's something that helps the reaction proceed forward, but it's not used. It's not a reactant. It's not a product. A good example of this is manganese. So manganese actually catalyzes, actually, let me give you a better example. Yeah, manganese works. Okay, manganese is used to catalyze the decomposition of hydrogen peroxide. So the manganese is not a reactant. It doesn't actually react with hydrogen peroxide. It's not a product. It's actually unchanged through this reaction. Actually, at the end of this, what we can do after we have decomposed hydrogen peroxide into its products, what we can do is we can take the manganese out of the solution. We can dry it off, rinse it off, dry it off, put it back in the bottle, use it the next year because it's never actually used. Manganese is really expensive. And when I asked to buy it in the science department, I got some kickback because it's pretty expensive to buy. And the way that I justified the purchase was by telling them we need to buy it once. And as long as nobody accidentally throws it away, we'll never have to buy it again because it's a catalyst. It's not a reactant. It's not a product. It's not used. It's not broken down in any way, shape, or form. It just helps the reaction proceed forward. So how does it help it proceed forward? Well, we'll talk about that once we get through mechanisms and we come back to catalysts. So I just didn't want to drop the word and then not come back to it. Okay, next thing you have to know for mechanisms is that each of the individual steps can have its own rate law. So some steps can go very fast. Some steps can go very slowly, and we can actually write individual rate laws for these individual steps. Now, the way that we write these individual rate laws for these intermediate steps, the steps of a mechanism, is different than how we write the overall rate law for the whole reaction. So, for example, if we are going to write the rate law for an overall reaction, that's what we've been doing this whole chapter, right? So if we want to write the rate law, meaning an instantaneous rate for an overall reaction, we have to have data. We have to have either the method of initial rates data, where we have a bunch of different trials that were run and we can compare the trials compare the rates and the concentrations for each of those trials, right? We can use that data to write a rate law, or we can collect data on the time and the concentration, right? And we can use that and graph it and figure out what the overall order is, and then write the rate law for that reaction. So the rate law for the overall reaction has to be based on some type of experimental data. This is not the case for individual steps inside a mechanism. The rate law for the individual steps, because they represent the reaction that's actually happening, what molecules actually collide, what molecules are actually formed, we can write the rate law from the individual steps. So take a minute and let that sink in, because those are two very different scenarios, right? It might be worth pausing the video here and doing a Venn diagram, similarities and differences for rate laws between an overall reaction and rate laws for the individual steps of a mechanism, and trying to think through, why can't we write the rate law of an overall reaction from the balanced reaction? Why can we write the rate law for individual steps off of the balanced reaction for the individual steps? Those two things represent vastly different things in the experiment. The overall reaction represents what you start with and what you end with, and doesn't represent anything that actually happens in the middle. The individual steps actually represent what's there in the beginning and what's there in the end, because they are the middle, right? And so for this reason, we write the rate laws differently. So you really have to wrap your brain around that. Otherwise, it's very easy to get confused and write the wrong rate law, or be looking for data when you don't need it, etc. Okay, so with that said, now let's look at some individual steps and how we can write the rate law from the individual steps. Okay, so here's our step, right? We have A going to products. It's a unimolecular step. And so the rate law is just going to be rate equals K always and forever, right? And then you're also going to have that multiplied by the concentration of A. So notice the reactions in the reactants in the reaction match what you see in the rate law exactly. This is not always true for an overall reaction. Also, the coefficient of the reaction for the individual step matches the order for that you see in the rate law. Again, something that's not true for or not automatically true for the overall reaction and the rate law that comes with that. Okay, so what's the molecularity of this reaction? It should be bimolecular, because there's two molecules in the reactants that have to collide in order for this reaction to go forward. And so again, the rate law is going to represent both of these reactants and their coefficients. Now, you can also write a bimolecular reaction with like we talked about with HI, when you have two of the same. And in that case, notice that the rate law represents the reactants, and the coefficient 2A goes to product is going to match the order A raised to the second. Again, something that's not true for writing the rate law for an overall reaction. Okay, what is the molecularity of this reaction? It is termolecular, because there's three things, A, and B. And then the rate law is going to represent this. You should have an A with an order of 2. You should have a B with an order of 1. So we can write the rate law for an individual step of a mechanism by using the coefficients and the reactants. This is not something we can do for the rate law for an overall reaction. The rate law for an overall reaction has to be based on data, because the overall reaction does not actually represent everything that's in that occurs inside that reaction. It only represents the beginning and the end. Okay, so now we can use this information to evaluate mechanisms and figure out what mechanisms actually occur or could possibly occur, and what mechanisms cannot possibly occur. Okay, so for example, here is a reaction. You have your overall reaction here at the top. You have your observed rate law off of this reaction. Okay, and what we want to do is we want to evaluate what kind of mechanisms could possibly be true and what kind of mechanisms could not possibly be true. So, for example, could this be a one-step reaction? If it was a one-step reaction, our steps in the mechanism, we would only have one of them. Step one would be 2NO2 plus F2 goes to 2NO2F, right? Okay, so if that's our only step in the reaction, then we should be able to write a rate law off of this balanced reaction, right? So let's do that. Pause the video here, write the rate law off of this one step in the mechanism, and then see if it matches what I write. Okay, so that's the rate law for this specific step in the mechanism, right? So if this is the actual mechanism is a one-step mechanism, then this has to be the one step, and this would be the rate law that would come off of my one step. Now, does this rate law match the experimentally observed rate law? No, it doesn't. They're not the same. And so I can say with certainty that this reaction is not a one-step reaction. It must be a 2 or 3-step reaction, because that would explain why the rate law, the observed experimental rate law, is different than what we would see in a one-step reaction. Okay, so here they're going to say the same thing. All right, so our next step then would be to try to work out a mechanism that does match the observed rate law. Now, again, you're not going to have to propose the mechanisms. All you're going to have to do is defend the mechanism and say, yes, this is a possible mechanism, or no, this is not a possible mechanism. Okay, so let's look at another possible mechanism. Since we know that this can't be a one-step reaction, let's look at this in terms of a two-step reaction. Okay, so again, you can see the same overall reaction at the top. You can see the same rate law. Remember, they gathered data and determined this experimentally. So let's look at a possible two-step mechanism. All right, so here's one reaction, and here's a second reaction. So notice a couple things. First of all, you can add these two together, and when we reduce out the intermediates, like atomic fluorine, we're going to get the same overall reaction. 2NO2, F2 goes to 2NO2F, right? So it's valid in that way. We can add the two steps together and get our overall reaction. Now, they have, in this proposed mechanism, they have also said that we have a slow step and the fast step. And this is usually true. In a mechanism, usually one step is slow and the other step is fast. So it's kind of like, you can go to the analogy of like cars driving down a road, right? If you have a super awesome car that looks like a box, and this car is really fast. Let's say you have a Formula One race car driving down the road, right? You can get from point A to point B super fast because you have a super fast car. Unless part of the road slows you down. Let's say you have a 8-lane highway here that you can drive your super fast car on, and of course, it has other possibly not as awesome cars. Oh my gosh, my cars look like shoes. That are driving with you, right? Well, no matter how fast your car is, if at some point in time your road goes down to 1 lane and then back open to 8 lanes, your car has to slow down and wait in traffic. Oh, my cars are getting worse. Okay, I'm going to draw a good car. Are you ready for this? That's the best car I have for you. That one was way better than the others. Still not exceptional, but we'll take it. Okay, so it doesn't matter how fast your car can cross this first section of the road or how fast it can cross this section of the road. What determines how fast your car can get from point A to point B is the slow part of the road. It may take 0.5 seconds to cross here and here, but if this takes 2 hours, then your trip's going to be 2 hours. It doesn't matter how fast it can go in the beginning or the end. And the same is true with reactions. It doesn't matter how fast NO2 and atomic fluorine can combine to form this product, because if this first section is slow, then it's going to drop off. Let's say this first section drops off 1 NO2F and 1 atomic F every hour. 1 per hour. And then this second section happens in a millionth of a second. Okay, the second part happens super fast, but it doesn't really matter because the first part, your slow part of the reaction, is going to determine the rate of your reaction. And so again, like I said, most mechanisms are like this. Most mechanisms have a slow step that determines your rate. It is the rate determining step. And then it has a couple fast steps that don't really matter because the whole rate hinges on the slow step. So if we look at this, this matters. This matters in a big way. If we look at this and we can write rates for the individual steps of the mechanisms, right? So we can have a rate for step 1 equals the K for step 1 times these two reactants. So NO2 raised to its coefficient, which is a 1, times F2 raised to its coefficient, which is a 1. So that's the first step. Then I can write the rate for the second step. K2, because the two steps are going to have different Ks. NO2 raised to its coefficient, which is a 1, times F raised to its coefficient, which is a 1. Now notice in one of my rates that I have written, I have an intermediate, right? Which can't be in the rate. So there is a way to get rid of that intermediate that we'll talk about, but not yet. I don't want to talk about that yet. So hang with me and let me make my point here, and then we'll deal with how to get intermediates out of the rate law. Okay, so if we look at this slow step, this is going to be the rate determining step. So the rate law for this mechanism has to match the rate law overall. So does it, is the question. And if it does, then this is a possible mechanism. Again, we can't really verify and say, yep, this is the mechanism, but we can say, yeah, this could possibly be the mechanism. So does it match? Yeah, it does. The two match. So this is a possible mechanism. Okay, before we get to that detail of getting that intermediate out, let's flip this and see what happens. Okay, so same idea, but now we flipped it, where this is the fast step and this is the slow step. Okay, so again, we have to look, does our mechanism predict the overall rate law? Does the mechanism match with the experimentally determined rate law? So again, our rate determining step is going to be our slow step. So basically what we're asking is, does the rate law we write for the second intermediate step match the rate law for the overall reaction, the experimentally determined rate law for the overall reaction? So let's see. Rate equals K2 NO2 F. Okay, so here is where we have to deal with that intermediate. So this comes down to an idea about the fast rate. And basically, we have to make an assumption. And our assumption is going to be that this reaction goes forward at so fast, and these products stack up and so much that it actually, the products start to collide and create a reverse reaction. And because this reaction, this first reaction, is so fast and is going to stockpile these products so fast, which then collide and create a reverse reaction, eventually it's going to hit an equilibrium where the rate forward, we'll go rate 1 for forward, is going to hit a point where it's going to be equal to the rate going backwards. Let's use a -1 for going backwards. Okay, this is what we call equilibrium. We've talked about equilibrium before. We're going to talk about equilibrium in a lot of detail next chapter. But for now, this is basically the concept. Rate forward equals rate reverse. Okay, so we can use this to get rid of this intermediate. Let's write the forward rate. So rate of this intermediate step going forward would just be K NO2 F2, right? The rate going backwards will go -1 equals the opposite, the inverse of K with the products. NO2F. It's like I flipped the reaction and I'm writing the rate of that flipped reaction, right? So if these two things are equal, then we can set these two equal to each other as well. Let me switch colors so you see what I'm doing. K -1 NO2 F. All right. And now we can solve for that intermediate and plug in what we solve for into our equation. Okay, so I'm going to isolate F by itself. So I'm going to divide both sides by everything that's next to F. Okay, so now I have something that I can plug in place of F. So this rate law becomes K2 times K1 divided by K -1. I'm not going to have enough room. Let me write it at the bottom, actually. So this rate law up here in pink becomes K2. I'm just putting all the K's together. K -1. Okay, now next to K2 is NO2. Now in place of F, we're going to have NO2 again So we can square that. F2 over NO2F. Now it's a little unusual because we have a product in there, but basically we have our rate law, which is equal to sum K, NO2 squared, F2 to the first order over our product. Does it match our experimentally observed rate law? No, it does not. It's close, but it doesn't. NO2 isn't squared, and the product isn't part of this rate law. And so this mechanism, this proposed mechanism, does not match. Now, it's not always this complicated. It was only this complicated because we ended up with an intermediate in the rate law that we had to get rid of. So we'll go through this again. We'll take a look at a couple different mechanisms and evaluate, are they possible or not possible? And then we'll go through this again too. What do you do if you have to get an intermediate out of the rate law? Okay, so process this, practice this. Let me know what questions you have. I'll see you in class.